So today we are going to get even more specific with our rational functions. We are going to graph these using our graphing calculator, but before we do any of that, we are going to calculate our vertical asymptotes, our horizontal asymptotes. We're going to also put in x and y intercepts, and if we have a graph that has a max or a min, or relative max or relative min, we're going to use our calculator to figure that out. So a major point from yesterday, besides how to calculate vertical and horizontal asymptotes, is we should do all of these calculations first before we put these on our calculator. Because for one, these, especially when you start throwing quadratics into the rational functions, take on a different type of graph, and we have to know what to expect. Sometimes our calculator doesn't give us the true graph. So let's take a look at example 1 here. We have a rational function. And before we put this on our calculator, we are going to calculate the horizontal and vertical asymptotes, and we're going to calculate the x and y intercept. So vertical asymptotes is where this is undefined, so I factored this. And this is undefined at x equals -3 and x equals 1. We don't write vertical and put 3 and -1 or -3, 1. We write them as vertical lines. Horizontal, remember you compare the degree of the numerator to the degree of the denominator, so degree is less, so automatically anytime that happens, the horizontal asymptote is y equals 0, a horizontal line. So the y-intercept, we know we can find that out by putting in 0 for x, and all of these would drop out except the 2/3, so my y-intercept would be 0 2/3. Now how do I find the x-intercept? Well, first of all, I may want to rewrite this as f of x, as y rather, and we know an x-intercept we're going to put in 0 for y. So now I have to solve for x, so I'm going to clear my denominator. That's going to get the denominator to drop out by multiplying both sides, solve, and I get -2. So my x-intercept is -2, 0. Now, on this one, we could have graphed it. I just wanted you to find this information to help us graph. All right, so directions in example 1 were just to find this information. Now, example 2, we are going to do everything to this. We are going to we're going to graph it. So the ultimate goal is to give an accurate graph. So we're going to do this by finding the vertical asymptotes, the horizontal asymptotes, any intercepts that we can have. And then we're going to describe beginning and ending behavior. So remember, that's like giving directions. So let's take a look here. All right, so first of all, make sure in example 2 you change it to x squared minus 5x plus 6, change the denominator. All right, so the first thing, this is the order that I would do these in. I would find my vertical asymptotes or where this is undefined. So this does factor into x minus 2 and x minus 3. So I have a vertical asymptote at x equals 2 and x equals 3. I compare my degrees. My degree of my numerator is less than the degree of the denominator, so I have a horizontal asymptote at y equals 0. All right, my y-intercept, I put in 0 for x, and I get 5/6, so I have 0 5/6. All right, my x-intercept, now I didn't show all the work, but I would make this equal to y and put in 0 for y, multiply both sides by my denominator, it drops out, solve for x, and I get -5/0. Now, if we were in class, what I would be doing is, I wouldn't be graphing, putting in the blue graph, I would draw my x and y axis, and I would graph my vertical asymptotes and my horizontal asymptotes, and I would also graph my intercepts. Then, finally, I would put this on my calculator. Because if you put it on your calculator, these graphs are sometimes misleading on the calculator. Having the asymptotes helps you put the pieces together. Now, something else. Some of these, when you have 2 vertical asymptotes, that is telling you that there are 3 parts to this graph. So if you put something on your calculator and you only see these 2 curves and you have 2 vertical asymptotes, that means that part of your graph is missing, and that means you need to adjust your y-axis. Okay, so if this doesn't show, you know something is wrong and you need to lower your y-min. All right, so something else that I want to point out. We do have a horizontal asymptote of y equals 0, but do you notice that the graph does cross the horizontal axis? Or the horizontal asymptote. Remember, a horizontal asymptote is not where it's undefined. It is a boundary, and the analogy I used yesterday is that when you have a riverbank, a horizontal asymptote is like the banks of a river. Sometimes the river flows along it and never crosses it, but sometimes it does cross it if it gets a lot of rain and it gets high. But regardless, the horizontal asymptote is still a boundary that this curve is going to travel along. So now, how do I describe all the behavior? Okay, so this is where we talk about left and right of our vertical asymptotes, because there's definitely a left side and a right side. So as x approaches 2 from the left side, f of x goes to infinity. As x approaches 2 from the right side, f of x goes to negative infinity. As x approaches 3 from the left side, f of x goes to negative infinity. And as x approaches 3 from the right side, f of x goes to infinity. Now, something else that I want to bring up is, how do you describe behavior around a horizontal asymptote? Well, since our horizontal asymptote, there is no left or right side, all right, we know that a horizontal asymptote is x is going to go to infinity and x is going to go to negative infinity. So instead of writing out two different statements, we just say as the absolute value of x goes to infinity. That takes care of going to positive and negative infinity. Well, in this case, your y coordinates will go to 0. So I know this crosses, but it's still going to approach it. Now, I did not calculate this, but you can see we do have a local max. So though we learned how to calculate maxes and mins using derivatives, these are more complicated. They're not basic power rules. So you can go back to your calculator and remember, go to second calculate max, and you could figure out this local max. Okay, let's go on to 3b. So we're going to do everything to this graph. We're going to find asymptotes. We're going to find intercepts. We're going to talk about beginning and ending behavior. All right, so again, before I put this on my calculator, I do all my calculations first. Asymptotes, intercepts, etc. Okay, so I'm going to see if my denominator factors what would make that 0, and it does. It factors into 2x plus 1 and x minus 1. So I have a vertical asymptote at x equals negative 1/2 and x equals 1. All right, horizontal, I compare the degrees. Oh, they are the same, so I take the coefficient. So I have a horizontal asymptote at y equals 3/2. So that is not going to show on your calculator. So again, we graph our asymptotes prior to putting this on our calculator. My y-intercept, if I put in 0, I'm going to get 0.8. My x-intercept, if I would have to use the quadratic formula. If I multiplied both sides by this, I would have to use the quadratic formula, and I'm not going to have you do that. We could probably approximate it from the graph. Now, go ahead and put that on your calculator, and remember, at any time, if you need to stop the video before we move on, or are there any times you need to replay it, please feel free to do that. So now is the time that I would put this equation on our calculator, but I would go ahead and what I have in black, I would have my x and y axes graphed, and I would have my asymptotes graphed, all right, and my intercept. All right, so now the fact that I have two asymptotes means I'm going to have 3 distinct curves in my graph. All right, and I can see that I do have a local minimum, so I could go to calculator and use second calculate and find my minimum, and I get about 75,007.92. All right, so how do I describe my behavior? As x approaches negative 1/2 from the left, f of x goes to negative infinity. As x approaches negative 1/2 from the right, it goes to positive infinity. As x approaches 1 from the left side, it goes to positive infinity. And as x approaches 1 from the right side, it goes to negative infinity. The horizontal asymptote, remember, there's no left or right. We know that x is going to go to infinity and negative infinity, so we just make it one statement. We know that the y coordinates will then head to 3/2. Okay. Now, let's turn the page and let's take a look at example 4. So how do we look at this? And how can we now know if we have basic transformations? Not problems like we just did, but if we have basic transformations from our parent graph, how can we know what to expect? So connecting transformations to rational functions. So here's our parent graph. So if I have 1 over x minus 3, doesn't that mean that that's translated right 3? But now let's also relate it to our asymptotes, okay? We know we're going to have an asymptote at x equals 3. So this is a combination of knowing what we know about asymptotes, but also talking about transformations. So I know that this would be my parent graph, but it would just be translated right 3, so I would now have a vertical asymptote at x equals 3. Now let's take a look at b. This is a nice transformation form, isn't it? Doesn't it tell me that this is translated left 1 and down 3? I mean, just because the negative 3 is here, it still means it's translated left 1 and down 3. So I know that I am going to have a vertical asymptote at -1. However, if I need to compare degrees for a horizontal asymptote, don't I have to have a rational function? And if I want to see, so if I want to compare degrees, I've got to have a rational function. So this is why we did this yesterday on day 1. If I asked you if this was a rational function, didn't you have to get a common denominator? So I multiply the numerator and denominator by x plus 1 over x plus 1, distributed, added my like terms, and I got -3x plus 2 over x plus 1. So go back to knowing what we know about asymptotes. X is -1 is my vertical asymptote. Compare degrees, and I get y is equal to -3. Does that also make sense based on that we said it was moved left 1 and down 3? So this is great for naming transformations, but maybe not as great for being able to look at and name asymptotes. So now let's take a look at C. All right, so this is great for naming asymptotes, isn't it? Isn't the vertical asymptote -3 where it's undefined? Degrees are the same, so the horizontal asymptote is 2. However, how do we know we don't have other transformations like reflections or vertical stretch or shrink? So how do I take a rational function and put it back in nice transformation form? You guessed it, long division. All right, I told you we never do anything just for the heck of it. Long division. I'm going to take 2x minus 1 and divide by x plus 3. What do I multiply x to get 2x? I get 2. So 2 times x plus 6, subtract, and I get -7. So this is also why we learned how to take a quotient and write it over the remainder, or to write the quotient with the remainder. So f of x would be 2 minus 7 over x plus 3. Now let's think about transformations. Doesn't that tell me it's moved left 3? Doesn't that relate to x equals -3 being the vertical asymptote? Doesn't this tell me this is moved up 2? Doesn't that relate to this being a horizontal asymptote at 2? However, doesn't this also tell me that it is reflected? So the branches would be going the opposite direction. And doesn't this tell me there's a vertical stretch of 7? So in this form, it's great for asymptotes, but it doesn't tell me all of the other transformations. In this form, it's great for telling me transformations, but doesn't tell me the nice form for asymptotes. Okay, last one. We are going to go to number 5 and do everything to number 5. So just to clarify some vocabulary, intermediate behavior, vertical asymptotes are in their own category. And intermediate behavior is just a fancy way to say, describe the behavior around the vertical asymptotes. All right, so we are doing 5A. So we're going to do everything to this. We're going to find asymptotes, intercepts, put it on our calculator, and describe behavior. Okay, so first thing I'm going to do is factor my denominator, and this would be undefined at 3 and -1, so I have vertical asymptotes at 3 and -1. If I compare degrees, numerator is less than denominator, so my horizontal axis is y equals 0, or horizontal asymptote is my x-axis. My y-intercept, I put in 0 for x, I get 2/3. My x-intercept, if I replace this with y, and then multiply by the denominator and solve that, I get 2, 0. So again, if you need to stop this first and then figure out everything and then play after you've done your calculations, do that. Okay, so now I'm going to graph in my asymptotes, I'm going to put in my intercepts, and now I'm going to put it on my calculator. So again, I have 2 vertical asymptotes. That lets me that tells me that I have 2 breaks in the graph, and I will have 3 sections to this graph. Now, there's no relative max or relative min. Let's describe behavior around the asymptotes. So as x approaches -1 from the left, y goes to -infinity. As x approaches -1 from the right, y goes to +infinity. As x approaches 3 from the left, y goes to -infinity. As x approaches 3 from the right, y goes to infinity. And a horizontal asymptote, I could make 2 separate statements, but we know as x goes to infinity or -infinity, this approaches 0. So now we have a good way of graphing these rational functions by finding vertical asymptotes, horizontal asymptotes, intercepts, figuring those out, then putting it on your calculator, and then going to calculate if you have maxes and mins. We know that once we start throwing quadratics into our rational functions, that we will have at least 3 curves, and that we should make sure that we check for missing parts.